welcome everyone to this session. Let's get started. So let me give you a brief update about whatever we done so far. So we are here discussing about the linear regression model. What is linear regression model and what are the linear equations? So far we all have understood that what is a linear regression, primarily what is regression, why it is known as linear regression. Okay, so you know that we are talking about the regression models, means we are trying to predict a target variable which is number. For example, if I have to predict the insurance amount for someone, or the EMI for a particular person, or the loan amount, right? Any number that I have to predict, like how much it is going to rain tomorrow, what will be the temperature for next 7 days. So any number that you predict is a regression. And there are multiple regression models. We are talking about linear regression model because the mathematical equation which is involved here is a linear equation of the form y equals to m of x plus c. So far, you are now clear that y is the target that we have to predict, x is the feature using which we will predict that target, m is the weight of that feature, c is the intercept, or you can say it is a bias which is associated to the model. Till now, we have understood that what are different steps involved in any model, machine learning model. For example, we gather the data, that is one. Then we look for duplicates in the data or missing values in the data. That means we start cleaning the data. After that, we have to do some feature engineering steps, right? Where we were saying, okay, let's do label encoding or data scaling and various other approaches like outlier detection. All these we have to do as part of our feature engineering. Finally, once we have the clear data ready with us, we have to split the data into two parts, the training data and the test data. On the training data, we train the model, and on the test data, we test the model, right? Before we take a decision that whether this model is really worth deploying into production, or we need to tune this model further or retrain this model on some more data, correct? So we have seen so far all these steps. But what we are going to look into today is the most important part of any machine learning model, and that is the evaluation phase. Means we train the model, okay, but when we train the model, there is something known as training accuracy, like how much is the training accuracy of the model. Then when we test the model, we look at the testing accuracy of the model, means how much accurate is the model in predicting something on the unseen data, right? Or how much is the error in the model, because based on these metrics only, we can take a decision whether this model is good or not. So ultimately, we have to check for the training errors and the testing errors before we can say, is this model really worth moving into production or not? Okay, so that's the most important part of any machine learning life cycle. So in the last session, we all discussed what is a linear regression model. It's a regression model using linear equation. We also discussed about the fit process, means where we train the model on the training data. But the important thing that we concluded after training the model was that the output of the training phase is the final equation. Okay, so till now I was telling you the equation is in the form of m of x plus c, right? But now let's think of it like this equation, which is a more accurate representation of a linear regression model. Simple linear regression model. Y equals to beta naught plus beta 1 x1 plus a small error. So this equation and this equation are same, it's just two different representation, guys. However, this is what we have to look in field of machine learning. So here we are saying y, the target that has to be predicted, is equals to beta naught. Beta naught here is nothing but our c value here, the c value, which is the intercept, okay, the constant or the intercept. Then the beta 1 x1, so x1 we know it is our feature, and beta 1 is the weight associated to that feature, and that is nothing but the m value or the slope value which we were talking till now. Is a good equation or a good representation we should be focusing going forward. Y equals to beta naught plus beta 1 x1 plus small e epsilon, or a small error associated to any modeling process. Okay, so this is also, you can relate it to the previous equation. Now if you have more features, so we will add here like beta to x2 and so on, right? So for example, using age and salary as two features, I have to predict the amount of loan this person is eligible for, right? So this is the equation we will be going forward talking. You can ignore this small e for the time being. You can understand this as error associated to any system which is doing some calculations. So that is this small error is. But now let's move ahead. So now you all are clear that this is a simple linear regression equation. So ultimately the intent of training the model is to find the values of beta naught and beta 1 using our training data. So once we trained the model, we saw that one of the output is the intercept value, which is nothing but the beta naught. In this case, it is minus 10K. And then the coefficient values means the weights associated to each and every feature. So in this particular use case, which we are doing, there are 6 features. Yeah. So guys, you can think of this as beta 1, beta 2, beta 3, beta 4, beta 5, and beta 6. And this is beta naught, the intercept, right? So far, we are all clear. We did this. But whenever we train a model, we always need to look at the training accuracy. Like what is the accuracy of this model during the training phase? Now, you must be thinking that why we need to do that, because training accuracy should be 100%. Why? Because there was the training data, there was this model. When I am passing the entire training data to the model, that means it is already aware that for this input, this is the output, right? So that means whenever you are training the model, you are passing the entire training data to it. Means with input, you are also passing the output. So model will always be 100% accurate, because for every input, it knows what was the output. Okay. So that means the training accuracy should always be 100%, because there was nothing hidden from it. The entire training data was available. Okay. Let's look at this. So there is this function, guys, score function. Okay. On this object, linear regression object, we have a score function which gives us the training score. We are passing the train x and the train y, means all the features in the training data and their corresponding target values. But see, you are getting 73% accuracy. Why? Okay. So when the entire data was passed into the model, it should give 100% accuracy, but that's not the case. So what's the reason for it? So most of the time, people are not aware that how the training phase works. So what really happens, guys, is that let's say this is your training data. Okay. And this is your model. Normally we think that we are passing the entire data to the model, the entire training data to the model for training, but that's not the correct thing. What internally happens during the training phase is the training data gets split into 2 parts automatically. You don't need to do that. Okay. And those 2 parts, guys, known as the training part, the actual training data, and the another part which is known as validation data. So remember, guys, this is your training data. You send it to the model for training purpose, right here. But during the training phase, what happens automatically is some part of the data, some part around 10% of the training data is kept for validation, and that is known as your validation set. And the remaining 90% of the training data goes for training. So consider that you had 100 rows in the training data. So only 90 rows will be used for training this model. Okay. But the remaining 10 rows will be kept. Kept for what? I'll tell you. So this model is trained on this 90% of the data, let's say the 90 records in this case, and then you get the trained model, guys. The trained model. This is your trained ML model. But when we were checking the accuracy of the training phase, remember, and that was coming 73%. How? So what happens is this 10 records will be used as if we are testing this model to find how good is this model in predicting these 10 records. Okay. So what that means is from this validation set, for these 10 records, we will only send the X part, the features, to this model, and model will give us the prediction, the predicted Y known as Y hats. Okay, Y hat. And then we already knew the Y part, which was hidden in this case. We compare Y with Y hat for these 10 records to tell you the accuracy of the training phase. So what is happening is, out of the total data, 70% was the training data, right? So, but in this case, consider 100 rows. Out of this 100, the actual training data is the 90% data, which we expose completely to the model. That, hey, these are the different scenarios, input output combinations, you learn from them. So model will always know about this as is, that for this input, this is the output. So you cannot test the model on this data because this was already exposed, both X and Y. So how can we test this model? We have a validation set kept, right? Which is 10% in this case. We can control that also. In some cases, 15%, 5%, we can do that also. But this 10% data is what, during the training phase itself, automatically model will send the X parts to see the Y hats, the predicted values, and compare them to the actual Y of this validation data to know, is there any error in the predictions, to identify the accuracy of the model. Okay. All this happens automatically. You don't do anything here. So all this process is happening during the training phase, which you see on my screen, right? But once you get the training accuracy of the model, let's say training accuracy comes out to be somewhere around 70%, right? 70% is your training accuracy. But what is the test accuracy? So we need to do the testing accuracy. For that, now you have the remaining 30% of the original data, right? This was 70%, but you have the remaining 30% data, which you have marked as test data, correct? On this test data, you will be doing manually the testing. And at that time, the accuracy you will get will be known as testing accuracy.
Okay.
And
But,
we have to compare, just to keep it clear, we have to compare the training accuracy with the test accuracy for some very important decisions. It is a very common thing now that will come to your mind. Then when we already have this validation set, which is giving us the accuracy here automatically during training, why I need to do this testing separately, right? So first of all, you guys should be very clear that during the training phase, also model generates something known as training accuracy, but it will use the validation set for that. And that validation set is nothing but the part of the original training data itself. And on that, model is giving you this training accuracy. By this, what we are going to know is that the model, when it is trained, it is having 73% accuracy. Okay. But now we will go into the second phase of the process, which is the testing phase, where we actually use the test data, right? So see what we were discussing, that we have the linear regression object, we will use the predict method, and then we will pass the testing data here to get the predicted output, or the Y hat in this case, right? So this is our Y hats. This is just a naming convention or the notation, Y hats for the predicted data and Y for the actual data. Okay. And then we compare these two. Okay. So now, once you have the predicted outputs, guys, the predictions, in this case, this is the predicted output. What you need to do here, we have to manually calculate the accuracy and the error. So let's check that. So first, let's check the test accuracy. So to calculate the test accuracy, we will be using certain packages and the libraries. So from the sklearn, there is a metrics module within which we have two methods, accuracy score and the R2 score. Okay. This R2 score is very important. We will talk about it. So the R2 score is the method which you have to use in order to calculate the test accuracy. So what I am doing, guys, I am calling this method R2 score. I am passing the actual data, the actual target of the test data, and the predicted data coming from the model. And here you can see that the test accuracy is 77%. Okay. So what we are doing here, we are calculating the testing accuracy by using some functions from the metrics package. We need to pass it the actual target from the test data and the predicted values from the test data. And this is the 77% accuracy. So this is the R2 score that you are getting. But now the next step is to compare our training accuracy with the test accuracy and take certain decisions about the goodness of fit, how good this model is. So training accuracy 73%, test accuracy 77%. So how to take decisions based on this is what we will be looking in this charts, the next charts, how to read these charts. Okay, so for the training
Okay.
accuracy, you don't have to do anything because it is already there. Simply call this score function, it will tell you the training accuracy on the validation set. But here for the testing phase, you have to first do the prediction, right? You have to predict the target first. Once you get the predicted values, let's say this is the first predicted value, which is 10,000. So for the first person, 10,000 is the let's say the loan amount or the EM amount that we predicted. Actual value was 8,900, right? But the model predicted 10,000. So that means there is an error in the model, right? If we look at the predictions, guys, the predicted value from the model for the first person is 10,000. For the second person, it is 3,600. But what was the actual value? Actual value was already available to us, correct? So it was 89,000. So there is some error in the model, right? You have to subtract the first two values, you will get the error, correct? So in this case, if
Yes.
you subtract from this actual, this 8988, you will get the error in prediction for this first person. And this is huge error, I would say. For the second person, you are saying, okay, he needs to pay you loan of 3,600, but actually it was 1,800. So this is almost double, right? That means this model has some issues, but at certain places it is good also, like 1,200, sorry, 12,000, here it is 14,000. So approximately it is okay. So some places it is good, but some places there are gaps. And that's where we cannot take the decision on the individual record, but overall we have to look at the total error of the model before we can take a decision that whether this model is good or not. So that's where the very first metric that we have to calculate is the accuracy score, also known as R2 score. There is something known as adjusted R2 also, guys. We will talk about it later. So R2 score, and then there is something known as adjusted R2 score. We will be talking about that later. But this is the function we use for calculating the accuracy. There is a proper formula behind it. In case you are interested, as I told you, always do question mark, and you will be able to get more details about this. And what is R2 score? Someone will say, hey, how you calculate the accuracy of linear regression? There is a important term for it known as coefficient of determination, guys, which is what we are using here to calculate the accuracy of the model. Now, you saw that at individual record level, if you go, definitely there will be some deviations between the actual and the predicted values. But we don't need to look at the individual records, rather overall for the all records, how good model performed, right? And that's where we are getting an R2 score. Now, the most important part, guys, is to compare the training score with the test score and conclude whether this model is a underfit model or an overfit model. That's a very important term. Whether your model is underfit or whether your model is overfit. What is the biasness in the model? What is the variance of the model? These are very key critical terminologies. So in this case, if we look at the training score and the test score, they are quite good. I can say that 73% is a good score for training, and for testing, 77% is also a good score. Definitely, these models can be improved further to give you 90% accuracies. That's one of the case, but still we can say this is a good model. Now, what would have been the cases where I would have said, no, this is not a good model? So let's look at those cases. Let's consider that your training accuracy was around 30%, okay? And the test accuracy was around 50%. In this case, we would say this is not a good model. Even if this is 50%, we would say, no, this is not a good model. Why? Because training accuracy is also low, test accuracy is also low. Even before test accuracy, training accuracy is something we should always focus on. If our training accuracy is around 50% or less, we would say this is an underfit model. Means this model is like a mere guess. 50% of the time it is good, 50% of the time it is bad, right? It is like a guess, a guesstimate. It's not a good model. it's an underfit. Even looking at these scores also, we can say it's an underfit model, because 50% accuracy or even less means this model definitely does not fit well on the data. Okay, but now when will we say this is an overfit model? Let's say during the training phase you get 90%, very high accuracy, but testing phase you get 60%. So there is a huge difference between the two. So the first thing is you will look at the training accuracy and you will say, oh, it's excellent. You will be very happy. But you should not. You should also look at the test accuracy. And the test accuracy is going very much down. Means there is a huge difference of 30% between the two accuracies. Means your model is not doing well on the test data. It may be doing well on the training data, but not on the test data. Means what is happening is the model is getting overfitted on the training data.